Hello everyone and welcome to our today's class. It is our first lesson on the topic reflection at curved surfaces. So as usual, let me comment by giving you the quote of the day, which states that procrastination is the greatest thief of time. So we'll discuss that quote at the end of our class today. So today we are looking at reflection at curved surfaces. So let's start by looking at reflection. Simply means the bouncing back of light when it hits an obstacle. Then a curved surface is just maybe a spherical surface or a circular surface. Then types of curved surfaces, or what we call the curved mirrors. So generally we have three types of curved surfaces, although we have the main two, which are the concave mirrors or concave surfaces, and also the convex mirrors or the convex surfaces. So these are the main two, but we'll look at three. So the types of curved surfaces or curved mirrors are the concave mirrors. We also have the convex mirrors, and also what we call the parabolic mirrors. So let's start by discussing the first type of curved surface, which is the concave surfaces or concave mirrors. So what are concave mirrors? So concave mirrors, they are also called converging mirrors. To converge is to bring together. So they are called converging mirrors because they converge the rays of light which are coming from different directions, then they converge them to a common point. Like for this case, this is actually what we are calling a concave mirror, because it is converging this ray of light and this ray of light which is incident on it. Then it is converging those rays of light, those two rays of light at a common point. So to converge is simply to bring to a common focus or to a common point. So we are saying that concave mirrors are also called converging mirrors. So concave mirrors, they converge the rays of light falling on them. They converge the rays of light falling on them. Then its reflecting surface, that is for a concave mirror, its reflecting surface curves inwards and the outside surface is silvered or polished. So as you can see here, the outside surface of a concave mirror, it is highly polished. So to polish is just to cover it with maybe some silver. So the outside is highly silvered or polished, while the reflecting surface, which is the inner surface, it is left unpolished. So we are saying that for a concave mirror, it is also called a converging mirror. Then it converges the rays of light falling on it. Then for a concave mirror, its reflecting surface curves inwards, while the outward surface is highly silvered or highly polished, so as shown here. So the outer surface is highly polished, while the inner surface is actually which is the reflecting surface, is left unpolished. Then two, we are looking at convex mirrors. So what are convex mirrors? So convex mirrors, they are also called diverging mirrors. So they are called diverging mirrors because they diverge the rays of light falling on it. So to diverge is to take two things which are together, then you focus them in different directions. So like for this case, we have two incident actually rays of light which are parallel to each other, but when they hit the convex mirror, they are diverged to different directions. So this one, before it gets to the mirror, they are actually parallel to each other, but immediately they hit the mirror, it is diverged upwards, whereas this ray is diverged downwards. So because convex mirrors diverge the rays of light falling on them, hence they are also called diverging mirrors. Then convex mirrors, they diverge the rays of light falling on it. Then for this case, the reflecting surface of a convex mirror curves outwards, and the inside is highly silvered or polished. So as you can see here, for a convex mirror, the inner side is highly silvered or highly polished, whereas the reflecting surface, which is the outer surface, is left unpolished. So the outer surface is the reflecting surface, whereas the inner surface is highly polished. That is for the case of convex mirrors. So as you can see here, I have identified this letter so that they can help you to know which mirror is actually the converging and which one is the diverging. So you have said that convex mirrors, these ones are also called diverging mirrors. Why? Because they diverge the rays of light falling on them. So like for example, if you look at this letter X, it is coming from a common point, then the rays are actually diverging. So actually the letter X can help you to know that a convex mirror will always be a diverging mirror. So you can see this point as the point where all the rays are emanating or emerging from, then they are being diverged, as shown by the letter X. They are being diverged outwards. And like for concave mirror, so I've also written V with the red so that it can also help you to differentiate or to know that a concave mirror is a converging mirror. So you can imagine these ones being the two incident rays of light coming from different directions, then they are being converged at a common point, or they are being focused at a common point as shown here. So in short, you are saying that convex mirrors are also called diverging mirrors. Then convex mirrors, they diverge the rays of light falling on them. Then for convex mirrors, the reflecting surface curves outwards and the inside surface is highly polished or highly silvered. Then we have other types of mirrors which we are calling the parabolic mirrors. Now, what are parabolic mirrors? So parabolic mirrors is the one whose reflecting surface curves inwards. So for this case, the reflecting surface is curving inwards, while the outside surface is highly polished. Then we are saying that parabolic mirrors is the one whose reflecting surface curves inwards and is a section of a hollow paraboloid. It is a section of a hollow paraboloid. So a paraboloid is usually, parabolic mirrors are usually made from cones. They are usually made from cones. Then maybe the difference between a parabolic mirror and a concave mirror is that, unlike for the case of a concave mirror where the rays of light are being converged to a common point, actually for the case of parabolic mirrors, the rays of light, after getting reflected on the surface, they emerge parallel to each other. So these are the incident rays. Then after it hits the surface, it emerges parallel. This is also another incident ray. Then after it hits the parabolic mirror, it emerges parallel. So the only difference between parabolic mirrors and concave mirrors is that one, concave mirrors are made from spheres, whereas parabolic mirrors are cut or they are made from a cone. Then the second difference is that for concave mirrors, the incident rays, after getting reflected on the surface, they are converged to a common point. Whereas for parabolic mirrors, the incident rays, after they hit the surface, that is the reflected rays, they emerge parallel to each other. Then two, we look at some definitions. We look at the definition of terms. So these diagrams will help us to know the definition or which term represents what. So let's start with the first definition, which is actually the aperture. So what do we mean by the word aperture? So an aperture of the mirror is simply the width of the mirror. So like for this case, the distance xy from x to y, this is what we are calling the aperture of the mirror. Then for the convex mirror, also the distance xy, that is the distance from point x to point y, that is the vertical distance from point x to point y, or simply the width of the mirror, that is what we are calling the aperture. So aperture of the mirror simply refers to the width of the mirror. It simply refers to the width of the mirror. Then two, we define what we mean by a pole. So when you hear of the word a pole in physics, it is usually denoted by capital P. So a pole is simply the geometric center of the mirror. A pole simply refers to the geometric center of the mirror. So like for this case, this is my mirror which is running from point X then to point Y. Then the center, the geometric center of this particular mirror, which is represented by capital P, is what we are calling a pole. For this case, the pole is here because this is where we have the geometric center. That is geometric center because a pole actually divides a mirror into two halves. For example, the distance from PX and the distance PY should exactly be the same. Also for this case, the distance PY and the distance PX should exactly be the same. So in short, the pole P is the midpoint of the mirror. So a pole in physics is defined as, that is for the case of curved surfaces, a pole is defined as the geometric center of the mirror. So a pole is the geometric center of the mirror. Then 3, we look at what we call the center of curvature. The center of curvature. So in physics, we denote the center of curvature by capital C. So the center of curvature simply refers to the center of the sphere of which the mirror is a part. So the center of the curvature is the center of the mirror, is the center of the sphere of which the mirror is a part. Now remember that this concave mirror and convex mirror, they are usually cut from a sphere. So it was a complete sphere, but they just cut one part, then they polished the outer surface, then they left the inner surface which actually reflects the rays of light falling on it. So imagine this one being a complete sphere. That is, imagine it was a complete sphere from here, then it actually covers here. Then we just cut a section of the sphere. So concave mirrors and convex mirrors are simply cut from a sphere. So imagine this was a complete sphere covering from this side, then to this other side. So the center of that sphere, that is what we are calling the center of curvature. So the center of that sphere, which was somewhere here, so meaning the distance from C actually to the pole should be the same as the distance from C to the other pole. That is which will be completing our sphere here. So this is just a section, but the whole sphere should be running this way as it is shown by my pointer. So that should be the whole sphere. So the center of that whole sphere from which the concave and the convex mirrors were cut from, that is what we are calling the center of curvature. So the center of curvature refers to the center of the sphere of which the mirror is a part. A part means it is equal. The two parts are equal. That is the distance from here to here, and the distance from center of curvature to the other end of the sphere, they are exactly the same. So we can simply conclude that the center of curvature is the midpoint. It is the midpoint of all points from a sphere, or any distance from the center of curvature actually to the sphere represents the pole or the radius of that sphere. So the center of curvature is simply the center of the sphere of which the mirror is a part. Then in case of a concave mirror, the center of curvature, that is C, is always in front of the mirror. So as you can see here, if this is our concave mirror, that means this is the outer side, then this is the inner side. So for the case of concave mirrors, the center of curvature is always in front of the mirror. So as you can see here, so the center of the curvature is always in front of the mirror. That is for the case of concave mirrors. Then conversely, the center of curvature is always behind the mirror. That is in case of convex mirrors. So for convex mirrors, the center of curvature will always be behind the mirror. So this is the front side of the mirror, then this is the behind the side of the mirror. So for the case of convex mirrors, the center of curvature, that is which is denoted by C, will always be behind the mirror. It will always be behind the mirror. Then 4, we look at what we call the principal axis, sometimes called the main axis of the mirror. So how do we define the principal axis? So the principal axis is just a line joining the center of curvature to the pole. So as you can see here, the principal axis, that is the principal axis, is actually this line, this black line here. So the principal axis is just a line joining the center of curvature to the pole. So this is our center of curvature, then this is our pole. So this line, this black line, which is joining the center of curvature to the pole, is what we are referring to as the principal axis, or simply the main axis of the mirror. So the principal axis is just a line joining the center of curvature to the pole of the mirror. Then also for this case, the principal axis is this one. It is joining the center of curvature to the pole of the mirror. Then 5, we look at what we call the principal focus. The principal focus, which is denoted by capital F. So the principal focus for a concave mirror, it is different with the principal focus for a convex mirror. So let's start with the case of a concave mirror. So the principal focus, which is noted by capital F. So F, this is actually what we are calling our principal focus. So for concave mirrors, the principal focus is defined as the point at which all rays parallel and close to the principal axis converge after reflection. So if you are asked to define the principal focus for the case of concave mirror, you simply say it is a point where is the point at which all rays parallel and close to the principal axis converge after reflection. That is, as you can see here, we have this ray being parallel to this ray. So the point where these rays are actually converging. So I have this ray, the incident ray, after hitting the concave mirror, it is converged at F. Then also this ray, it is parallel to the principal axis, but after hitting the mirror, it is reflected and focused at F. So a point at which all rays which are parallel to the principal axis converge after reflection is what we are calling the principal focus. That is for the case of concave mirror. So we are saying that for concave mirrors, the principal focus, which is noted by F, refers to a point where all rays parallel, or where it is a point where all rays which are parallel and close to the principal axis converge after reflection. So this ray is closer and parallel to the principal axis. This upper ray is also closer and parallel to the principal axis. So the point where they are converged after reflection on the mirror, this is what we are calling the principal focus. So the principal focus for concave mirror is a point at which all rays parallel and close to the principal axis converge after reflection. Then the principal focus for the case of now a convex mirror simply refers to the point at which all rays parallel and close to the principal axis appear to diverge from after reflection by the mirror. So as you can see here, I have this ray, and also this ray, which is of course parallel to the principal axis. So this is my incident ray, which is parallel to the principal axis. This is another incident ray, which is also parallel to the principal axis. Then after reflection, the rays are diverged upwards. This one is also diverged downwards. Then there is a point where all these rays are appearing to be emerging from. So the point at which all rays parallel and close to the principal axis appear to diverge from after reflection by the mirror is what we are calling the principal focus. So the principal focus for the case of a convex mirror simply refers to a point where all rays close and parallel to the principal axis appear to be diverging from after reflection from the mirror, or after reflection by the mirror. So a point where all rays close and parallel to the principal axis appear to be diverging from after reflection by the mirror. Then 6, we look at what we call the radius of curvature, which is denoted by small r, the radius of curvature. So what do we mean by the term radius of curvature? That is in reflection at curved surfaces. So radius of curvature simply refers to the radius of the sphere, is the radius of the sphere of which the mirror is a part. So the radius of curvature refers to the radius of the sphere of which the mirror is a part. That is, if we imagine this was the total sphere, imagine this was a complete circle or a complete sphere this way. That is the radius. Remember, the radius refers to the half the diameter. That is the distance from the center of the sphere to the actually to the circumference of the sphere. So like for this case, if we said that the center of the sphere refers to the center of curvature. So the distance from the center of curvature to the pole is what we are calling the radius of curvature. So the distance from the pole, that is to the center of curvature, that is what we are calling the radius of curvature. So we are defining the radius of curvature as the radius of the sphere of which the mirror is a part. The radius of the sphere of which the mirror is a part. Alternatively, you can define the radius of curvature as the distance from the pole, the distance from the center of curvature to the pole of a sphere. The distance from the center of curvature to the pole of a sphere. Then next we look at what we are calling the focal length. So what do we mean by focal length? In physics, focal length is always denoted by small f. So do not confuse principal focus and focal length. Principal focus is always denoted by capital F, whereas the focal length is always denoted by small f. So the focal length refers to the distance from the pole of the mirror to its principal focus. The distance from the pole of the mirror to its principal focus. That is this distance here. The distance from P to F, which is equivalent to this. So the distance F, the distance from the pole to F, that is the distance from the pole to F, that is this small f, is what we are calling the focal length. So focal length in physics refers to the distance from the pole of the mirror to its principal focus. The distance from the pole of the mirror to its principal focus. So it is also important to note that the the radius of curvature is always twice the principal focus. No, the radius of curvature is always twice the focal length. So focal length times 2, you get the radius of curvature. So if you take this focal length, remember focal length is the distance from P to F, and the distance from P to F is equals to the distance from F to C. So that means if you take focal length, that is the distance from P to F, then you multiply by 2, you will get the radius of curvature. So the radius of curvature is always twice the focal length. Alternatively, you can say that the focal length is always half the radius of curvature. It is always half the radius of curvature. So lastly, we look at what we are calling the focal plane. So how do we define focal plane in physics? So focal plane, it is a plane perpendicular. It is a plane perpendicular to the principal axis and passes through the principal focus. So as you can see, this is what we are calling our focal plane. So the focal plane meets the principal, this is what we are calling the principal axis. So it meets the principal axis at an angle of 90 degrees. So this angle should be 90 degrees. So meaning the focal plane is always perpendicular to the principal axis. So the focal plane, it is a plane perpendicular to the principal axis and passes through the principal focus. So as you can see here, my focal plane is passing through F. So F is the principal focus. So it is just a plane which is perpendicular to the principal axis and passes through the principal focus. So focal plane is a plane perpendicular to the principal axis and passes through the principal focus. Then also, parallel rays not parallel to the principal axis will always converge at a point on the focal plane. That is for the case of concave mirrors. So all rays which are parallel to each other but they are not parallel to the principal axis, they will always converge at any point within the focal plane. So as you can see here, the focal plane is represented by this line. So all rays which are parallel to each other but they are not parallel to the principal axis, they will always converge at the focal plane, that is after reflection on the mirror. So like for my case, this line is what is representing my focal plane. So we are saying that focal plane is a plane perpendicular to the principal axis and passes through the principal focus. Then we look at reflection of light by curved mirrors. So rays which are close and parallel to the principal axis, they always converge at the principal focus for the case of concave mirrors. So as you can see here, if you have any rays which are parallel to each other and also parallel to the principal axis, they will always converge at the principal focus. So I forgot to shade the outer side. This is a concave mirror, so the outer side should be shaded such that the inner side is the reflecting surface. So that's an error. Then here the inner side should be shaded because this is our convex mirror, so that the outer side is actually the reflecting surface. So we are saying that rays close and parallel to the principal axis converge at the principal focus for the case of concave mirror. So they always converge at F, or at the principal focus for the case of concave mirrors. But the rays which are parallel, the rays which are close and parallel to the principal axis, they always appear to be coming from the principal focus, that is for the case of convex mirror. So as you can see, after reflection, they appear as if they are emanating or emerging from the principal focus. That is for the case of convex mirrors. Then parallel rays not parallel to the principal axis meet at the focal plane. That one we have already stated it up there. Then lastly, we look at the principle of reversibility of light. So how does the principle of reversibility of light state? The principle of reversibility of light simply states that the path of light rays are reversible. So the principle of reversibility of light states that the path of light rays are reversible, meaning if a ray was moving from this particular side, then it hits, then it moves upward. A ray can also emanate from upward, then it hits the surface, then it comes there. Then also here, if the ray was emanating from here, then after hitting the surface it is reflected. Then if a ray comes through F, it will always be reflected parallel to the principal axis. That is what the principle of reversibility of light simply means. That if a ray is parallel to the principal axis, then after reflection it is being reflected through F. Then if you also have an array of light coming through F and hitting the surface, it will always be reflected parallel to the principal axis. So the principle of reversibility of light states that the path of light rays are reversible. The path of light rays are reversible. So we've come to the end of our class today, but we need to discuss the quote of the day. So the quote of the day stated that procrastination is the greatest thief of time. Procrastination is the greatest thief of time. So what does this particular quote mean? So the quote is warning us against procrastinating. It is also encouraging us to have some sense of urgency in everything we do. So a few years to come, you will regret more about the things you never tried than the things you tried and failed. And imagine this, imagine this. Suppose I gave you $1,440 every day, and I instructed you to spend all of them within a day. Otherwise, I will take them from you. Then I'm sure you will spend all of them wisely, even in less than 24 hours. So it sounds funny that most of us will spend it poorly if it was time. That is, if it was money, you will spend it well. That is $1,440. But if it was the same amount of time, that is 1,440 minutes, we will spend it poorly. So every day we are given 1,440 minutes to spend by the nature. So whatever you choose to do within those 1,440 minutes, it has a greater impact on your life. So be careful on how you spend every minute within the 24 hours that you are given. And remember that time is more valuable than money, because you can always create and recover lost money, but you can't create and recover lost time. And lastly, do one thing every day that your future self will thank you for having done it in your past. This is Kind Tuition Academy. Kindly hit that subscription button on YouTube. Thank you.